Right, the recorder is on. Let me check the audio part. It is recording. All right. So the first thing we'll do is we'll take a look at the homework assignment, especially for people who have not, finished it yet. It might be helpful. It's called long string. Okay, so let's do that. tar zzbf longstring.tar.gz. All right, so you have two functions to write in assembly, and both are now currently written, as it is, in the homework assignment. One is called L string, long string write, and the other one is L string, long string read. So basically, this is what you need to do. When you look at this code, some of these constructs are fairly, easy to deal with. We have dealt with some of these before. Like a local variable, we should know how to deal with that. Head is a pointer in this case. So in this case, we're getting a particular element of a member of a structure that is pointed to by a pointer that is a parameter. So it sounds like a lot of stuff, but you just have to do it one step at a time. Okay, that's really is the key, is to do it one step at a time, and don't try to look at the whole thing and go like, okay, I have not done this particular combination before, because each step is just by itself a step. Okay, so that's the write subroutine, and the read one is a little bit more difficult, not by a whole lot, just a little bit more difficult. And I think this is going to be the most troublesome part, okay, which is taking the address, not the content, of an element of an array, and that array in return is a member of a structure, and that structure is pointed to by a pointer. So in this case, we want to get to the address of the element and not the content of the element. So I think if you can figure out this one, the other parts will be relatively easy. Okay, I wouldn't say they're like really, really easy, but I think they'll be relatively easy. So are there any questions about this particular homework assignment? Are there any particular lines that you find challenging? No questions? Now, sometimes having a picture really helps, okay? So if you think about a picture, I'm going to draw it on the whiteboard, because you might find it useful for the quiz question that we'll be dealing with. In about 10 minutes. So what I'll do is I'm going to draw you the content of memory. Okay. So now we have basically two memory spaces. One is the heap. Okay. The heap is basically where things are allocated when you call malloc. Okay. They're allocated from the heap. This is the stack. The stack is what we have been using all along for the past few weeks. Okay. So in this case, on the stack we have our PTR, which is a pointer. It is a parameter, and from the previous homework assignment, you kind of know how these things are arranged. So after pointer, this is high memory. So this is high address in this direction up. So right after the pointer is pushed, we have, in this case, we have the file descriptor, which is the first parameter, and then we have the return address. And after the return address, we have the saved old EBP. And old EBP is saved by the subroutine. It's not done by the caller. The caller is responsible for the pointer, for the file descriptor, and also the return address, because the call instruction is what is pushing the return address. The callee, the subroutine, in this case LSTR, long string read, is responsible for old EBP. And then below this, we can potentially have local variables. So local variables would go here, okay, like so. So when we look at that line of code that is highlighted, which is on line 17, it's basically saying these 4 bytes over here is a pointer. In other words, it is the address of somewhere in the heap, because we know that we are allocating from the heap, because that's what line 12 is saying. Is that okay? Actually, this is not accurate. I'm sorry about this. This is actually head. You which is a pointer to a pointer, and one of the local variables is a pointer, is PTR itself. So PTR is the one that points into heap. So I apologize. So this is the correct picture. Head points to somewhere else, okay? So whatever head points to would also now be pointing to the same place in the heap. But for the time being, we'll just pay attention to PTR and not head, okay? PTR is a pointer, it's just a regular pointer. On line 12, PTR gets the address returned by malloc. So in malloc, we allocate a chunk of memory. So this entire chunk of memory is a struct long string node. So this is a LSTR node, like so, okay? And PTR points to the very first byte of a LSTR node. Chunk is one of the members. Now, whether chunk is the first member, the second member, or the last member really does not matter, because chunk can be just some portion in here. So we'll call this chunk. And the way your program is supposed to work is you should have another program to generate the necessary labels so that you know where this place is using its name, which is LSTR node underscore chunk. So this label is basically the displacement or the offset from the beginning of a structure to this particular member. Are we still doing okay so far with this? Is that okay? So this means if you can follow PTR, which is a pointer to the entire structure, and then use LSTR node underscore chunk to locate the beginning of this member, then you can find the address of chunk as an array of inside the structure. But once you know where's the beginning point of chunk, then indexing is easy because it's an array of characters. So you just have to add I to the address of chunk itself to get to the address of the element that you need to access. Are there any questions at this point? I'm not going to show you the exact instructions, partially because it is a part of the quiz, okay? But this is how things look like when you draw it out in as a picture. So I is just basically saying how far do we need to go from the beginning of chunk to get to the one element that you need to access. That's basically I, which is the index into the element. And because it is an array of bytes or array of characters, finding that location is pretty easy because there's no scaling involved in this case. So are we kind of doing okay so far with this one? Because I think this probably is the hardest part of LSTR or long string read. The rest of it, not too bad. This one looks kind of nasty, but if you can do it with one step, it's just a repetition to do it the second time. Okay, because it's really just locating a member of the structure pointed to by a pointer, and you have to do it one more time to get to the other one. All right. Are there any questions at this about this particular subroutine? So whenever you have any doubts, or when you're planning out, how to write the code, drawing a picture sometimes helps. It depends on how you think. But for people who like to look at a picture or they like spatial stuff, having a picture definitely helps because it shows you how to get to a certain place. PTR points to the first byte of a structure. From the first byte of a structure, you add LSTR node chunk to get to the first byte of the member chunk. And then from the member chunk itself, you add the displacement or the offset of I to get to element I of that array. Yep.
So this only works for read, correct?
Mm-hmm.
Because in write there's no pointer?
In write there's a pointer too, except we don't have a pointer to a pointer. So let's take a look at write. str write. Oops. Okay, so in the write subroutine, there's It's a similar structure because you still have to use the address of the byte to use a system surface number 4 instead of 3. But it's the same thing. It's really the same setup. The only difference is in LSTR write, there's no pointer to a pointer. It's just a pointer to LSTR node. Okay. Any other questions? And don't forget, do not use EBX. If you are using EBX in your subroutine, you have to save and restore EBX. That's the one thing that people get bitten by, most of the time is using EBX but not, restoring it, after you're done with it. EAX, ECX, and EDX are free for you to use, but do not expect the registers to be preserved. So when you call malloc can potentially change ECX and EDX. It will certainly change EAX because that's the return value of malloc. Okay, so any other questions related to the implementation of the subroutines?
Don't we have to use EBX to use the write call?
Say again?
Don't we need EBX to use the write call?
Yes. So that means you will need to save and restore EBX. To save and restore a register means you just push it before you change it, and then after you're done with it, just pop it. All right, we're getting close to 9:15. So any other questions before we start the quiz? No questions? Right. I think the question is like this one, what I just talked about. But it is actually easier because I don't think I asked for indexing in that case. Did anyone download, any of the files that are on Moodle, for this class? Like, let's see, there are a few files that I have posted here. I did not bother to remove these files. One is bst.tar. Did anyone download it and take a look? No one is curious. Okay. BST stands for binary search tree. So it's a data structure, usually taught in cisp 430 or so. It's a recursive. It has recursive subroutines to construct, traverse, and also print from a binary search tree. So if you look at that one, that's actually not a bad one to take a look at, because it has the C subroutine on one side and it has the assembly code on the other side. This one is already solved. Okay, in other words, you can actually just compare the assembly code with the C code and find out how a particular thing is implemented in assembly when the C code is given to you. So it would not be a bad idea to take a look at bst.tar. LList is a linked list, that is already sorted, and that one actually has some relationship with your homework assignment. So it wouldn't hurt to take a look at llist.tar.gz. Once again, it has the assembly code on one side and then the C code on the other side. This is the solution to homework assignments from a previous semester. So that might not be a bad idea, just to get you ready for the final exam. You're always welcome to check out the video recording from past semesters as well, because all of these were explained in past semesters. So in case you are interested in what I taught in previous semesters, it's always available. All right. All right, the time is getting close. I'm going to refresh and open up the quiz in this time. Some of you actually, already know the answer to this question, because from the answer from the previous quiz question, I know some of you already know the answer to this one. It's just, oh, okay, it's actually easier because you don't need that last step from the previous homework assignment. You know who you are. When you look at the question, you go like, oh, okay, I got it done already. All right, so I'm going to refresh it and click on it. All right, so I'll just spend a little bit of time to, well, first close the door. This is the lead blower. It will be me this afternoon. On the roof, you're blowing leaves. My wife said one of these days you're going to fall from the roof. So let's hope that's not the case. Okay, so in this case, I have certain symbols that are predefined. So PTR is a symbol defined as the offset from where EBP points to a parameter PTR, which is a pointer to a struct X. So it is very similar to this one here, except this one is a local variable, and the one that is your question is a parameter. Okay, X underscore A is a symbol defined as the offset from the beginning of a struct X to a member A. So A is the name of the member of a struct X. So that is kind of the same thing as LSTR node underscore chunk in this picture. EBP is already set up for a standard call frame. So you're already in the middle of a subroutine. You don't have to worry about how to set up EBP. You're already in the subroutine itself. EBP is already set up correctly. So your job is to write the code to compute the address of member A of the structure pointed to by PTR and store that in register EAX, which is kind of the same as what you did here, except you're not dealing with ECX in this case. Keep in mind that this time we want the address stored in EAX. not the content stored in EAX. Okay, when you're done, please put your pencil down so I can see whether the whole class is ready or not. I'm sorry if you're planning to draw something on a piece of paper just to pass time. Are we ready? Does anyone need more time? All right, let's go ahead and collect the answers. So let's find out what the answer is in this case. I'm hoping the first 15 minutes of the class is. I'm hoping some of you find those 15 minutes to be relevant to the actual quiz question here. Okay. So we have to start from EVP, okay? Because everything starts with EVP whenever we're dealing with something that is on the stack. EVP points here. Okay, because EVP, the frame pointer, points to the saved value of the same register from the previous, from the caller. Okay, so no matter whether PTR is a local variable or a parameter, the symbol is still defined as the offset from where EVP points to the parameter itself or to the local variable. So the way that works is the same. So the first instruction is move L, okay, have to, in this case the long is not necessary because one of the operand will imply the width of the operation. So the L is not actually needed here. So what you need to do is to do a move L PTR %EVP. This will access the parameter itself, and I'll copy that into EAX first. Okay, so that's the first instruction. Doesn't have to be the only way to do it, but this is one way to do it. So what that instruction will do is to make EAX basically an alias to point to the beginning of the entire structure. That's the first step. Is that okay so far? Okay, okay. So this is the first step. I'm just going to label it. The second step is to get to the beginning of the member itself. Well, we just have to go this distance, right? So the second instruction is going to be an add instruction. Going to be an add long. Once again, it doesn't have to be L. If you just say add, it's going to be okay. It's not a very good way to do it, but it will still suffice in this case. So it's going to be a $sign because it has to be an immediate operand, x_a, and then the comma to EAX. So what that would do is to move EAX, instead of pointing to the beginning of the entire structure, now it will be pointing to EAX, will now point to the beginning of the member that we want to access. So this is basically step 2. And that's it. 2 instructions. Are there any questions about this whole, the sequence of the instructions? Okay. Now there are alternatives, okay? If you don't want to use the base addressing mode, this instruction can be split into 2. So you can basically do a move L % EBP to EAX first. So that will make EAX points to this place, and then you can do all the calculations based on that by adding I think it's PTR, $PTR to EAX. So that will make EAX point to the parameter or the local variable PTR, and then you can do a move L indirect EAX to EAX. So this one single instruction can be replaced by these 3 instructions if you want to use the RISC type instruction instead of the cisp type instruction. Are there any questions about this part here? No questions? It's all good? Okay. And since the screensaver was active, I need to check to make sure that the recorder is still okay. All right. So as I said a little bit earlier, I'm just going to download these 2 files just to show you what is in the content, because I think some of you may find it useful just for review purposes, to get ready for the final exam, or maybe it's even useful for the homework assignment. So I'm going to download both of these files and just take a quick look at those files, and you can decide for yourself whether it is going to be useful or relevant or not. So the first one is BST, which stands for Binary Search Tree, and this one has got everything done already. So in this particular folder, there are there's one subfolder for the C program. The assembly version is it's not done here. It is not here, but it is in my notes. So what you need to do is to take a quick look at the date. It is May 8th of 2013. So I'm just going to locate a YouTube file for you. So we are looking at history, go to videos, and it'll take a little bit of time to look for it. I'm not sure whether the search function will work well in this case. That's going to be a long time. All right, let's see if I can. Does anyone have a calendar? What is the last? It has to be a Tuesday or Thursday when I talk about the solution. So, is anyone interested in the solution? Because I just want to locate the video that contains the solution to this particular homework.
Last Tuesday or Thursday?
Yeah. I need a Tuesday or Thursday after May 8th.
After May.
Yep. 13? Okay. So we'll try that, which is 2014-0513 cisp310. There we go. Nice. All right. So we'll try this one first. See if it is what we are looking for. So BST. This one is L list for the sorted. Not the one, maybe it's the 15th. Nope, there's nothing on the 15th.
I think it could be the 8th.
Sorry?
I think it could be May 8th.
May 8th. The 8th is probably when it was assigned, but we'll take a quick look. It's also the 2013, not 14. Oh, I was looking at the wrong year. Sorry. 13. No recording. But on the this is the one that has the L list. So if you want to look into the solution of L list, this should be the one. Let me see if the one that I have here is already the solution. So if it is, it's going to be. Sorry?
The L list has a solution.
Has the solution? Okay, so that would be the one to take a look at. So we can look at the L list here, and it has both the C code and also the assembly code. So make node has it has the solution of make node, but not the other ones. Make node does it have a C version of that? There's no C version for the make node.
I think it's in the name.
Okay, this is the assembly code of make node. And if I look at all the .c version, oh, okay, it's in main itself. Yep. Okay, thank you. So make node is this code in C, and then the other one is the assembly code. But if you watch the video, I think, unless this is the very last homework assignment where there's no lecture, to explain the answer, this one may have the solution also, in the videos. All right. So, are there any questions about, how to get the homework assignment done? How many people are running up against segmentation fault and all kinds of stuff like that? All right. Well, it happens. Okay, whenever you mess around with a stack and also with pointers, and this time we have a pointer to a pointer, you can run into issues like that. Okay. So what I'll do is, since there's no solution to BST, we'll go ahead and do it today. Okay. So we'll look at BST or binary search tree. And I'll let you guys pick, a particular function to implement today, okay? But we'll just do one. What I'll do is I'm going to let you guys take a look at all the different functions, and you guys can pick which one you want to deal with. This is BST destroy. It is a subroutine to deallocate an entire binary search tree. It is recursive, but don't let the recursion part bother you, because a call to a subroutine itself is no different from a call to any other subroutine. So this is a BST destroy. You might want to take a look at this and go like, is this something that I want to take a look at? And here is BST insert, which is a little bit longer, okay? But for the most part, it doesn't have any really truly unique features. The only thing that is unique to the BST homework assignment is we always deal with a pointer to a pointer, which is not what you have to deal with except for long string read, where you have to deal with a pointer to a pointer. The next one is BST print, which is does not involve pointer to a pointer. This is the easiest one of all of them. And this is BST read. Okay, has a scanf in it, but it's not really that big of a deal. And this is main, and I think that's it. Those are all the subroutines. And this is the include generation file, so we'll deal with this one too. So what do you think? Which one do you want me to implement? Take a pick. Come on.
I think read.
Oh, wait, second one, the insert.
The second one, the insert. Okay. Okay, so let's take a look at BST insert and see, is that what you guys want to do? Now remember, even though it is longer and it looks kind of nasty, there's a lot of repetition here because lines 9, 10, and 11, they're pretty much the same thing. Once you figure out how to do line 9, 10, and 11 are pretty much the same thing. Line 17 and line 21 are basically the same thing because they're both recursive calls. Is that okay? Is that what you guys want to do? Yep.
Is this for an assignment coming up?
Nope. This is a homework assignment from past semesters. Yep. But for preparing for the final exam, I think it will still be useful. All right. So let's go ahead and pick this one. Okay. All right. So the first thing we do is we use the makefile and make sure that everything can be made. And when you look at main.c, all it does is to read into the binary search tree, and then it will print it and it will destroy it. Okay. And the way it works is it's asking you for a whole bunch of numbers, integers in base 10. So you can give it an unsorted list of integers like that. Okay, it doesn't really matter how many. It can be as many as you want, and you can have duplicate entries as well. Okay, and then when you're all done, you type Control-D, or you can give it a file with the numbers. Okay, so you can do either way, and then it will print out everything in the binary search tree using a particular way to traverse the tree, and then as a result of that, it will print out all the numbers in a sorted way. Okay, so that's the entire program. It just reads a whole bunch of numbers, store the numbers in a binary search tree, traverse the tree and print out the numbers, and then destroy the tree, deallocate memory, and that's all it does. Okay, so the one that you guys want to deal with is the insert. But before we deal with the insert, we also have to deal with the one file to generate all the offsets, all the displacements, and that would be our node include generation file, which is this one over here. So this is the first file that we have to deal with. So we'll go ahead and edit that file, and also change main.c so that we can deal with we can use the header file. Let's see. Okay. And we want to display both side by side, so I don't have to go between the two files. Okay. So the first thing we do, which is something that you have to do as well, is to print the displacement of each member of a node in this case. So in this case, we have two members, or three members, excuse me, PL, which is pointed to the less than side, PG, which is pointed to the greater than side, and also the value of this particular node, which is V here. So we have to go like node underscore PL equals to %D, and then we do the calculation on this side. So the calculation is done by converting the address into a void pointer first. In this case, I need to have a local variable of a node type first. So struct node n. So we need to look at the address of the member PL, the address of n.pl, and then subtract. I know it's hard to see. Oh, it's wrapping around, so it's easier to read actually. So that would be the first line, and then we have three lines like these, and then the fourth line we do the size of. Okay, or you can just say size. And the size of is easier because you can just use the size of operator and ask for the size of n, and that should be it. We also need a new line for each one so that we have individual lines. Change the members. In this one's going to be PG, and then we have V down here. We have V down here. And get rid of all the extra stuff. All right, so I think this is all done. Let's go ahead and take a look at the makefile first. All right, so I think that should do it. All right, take a look at node.inc. And that's what it looks like. Each entry is a label definition, and the label is defined to be the number of bytes between a particular member of a node from the beginning of a node. Okay, so that's kind of consistent with all the stuff that we have been doing as well. All right. So once this is done, we can actually get started with the subroutine itself. And to do that, if you don't mind, I'm going to change the font size because I need to fit a little bit more text than usual, so I need to use a smaller font, maybe a 14. Is that still readable to all people in the back? Okay, so this is what we'll do. So we're gonna take a look at the C code first. Okay, so that will be bst insert.c, and we'll work on the assembly code on the side, on the other side. So bst insert.uppercase s, and so this is kind of neat because we can look at both source files at the same time. So we have node.inc to include the definition of the labels. .text is not needed, but it's a good idea to make sure that you're in the code section. .global bst insert to export the label of the subroutine. Then we define the label of the subroutine as well as the return statement. Yep.
Could you also do for the include file a define statement?
Say again?
Preprocessor?
Yes.
Define? Okay.
Yep. So in your project, the include file that includes the pound define, you can also pound include it here.
Okay.
Yeah, because it's just a preprocessor replacing all the macro references to the definition of the macros.
Mm-hmm.
So, and a C preprocessor, unlike what the name suggests, is not C specific.
Okay.
You can feed anything through a C preprocessor.
Okay.
All right. So, okay, we're on line 6 of the assembly code. Okay, so the first thing we do is to push EBP, and the last thing we do is to pop EBP. Basically, we're saving and restoring the frame pointer. And then the next thing we do is we move ESP to EBP, so this becomes our new frame pointer. And we do the reverse before we get out, so that we know where to find the old frame pointer to restore that. And depending on whether we want to use local variables, we also want to adjust the stack pointer at this point to subtract any amount that we want to reserve for local variable. In this case, we don't have any local variables, so I'm not going to do that. And now we are ready to work on the conditional statement. So the conditional statement in this case is a little bit awkward. It's not something that you guys have to deal with your homework assignment, because proot is actually a pointer to a structure. And I'm checking not whether proot itself is null or not. I'm checking whether what it points to is null or not. Okay, so it's a little bit more involved than your homework assignment, but I'm going to implement it just the same. Okay, so we'll go ahead and move along proot. I need some definitions here first. So the way I do it is always define OEBP to be 0. It's the displacement from where the frame pointer points to the old or the saved version of EBP. The return address is next to it, so it's old EBP plus 4. And then we have the parameters after that. So proot being the first parameter is next. And then we have the v being the next one. So proot plus 4. So this. I like to do it this way because this way I don't have to remember, oh, 8 is proot and 12 is v. Okay, so I can just refer to the name of the parameter. So I'm going to move proot EBP to EAX. So EAX is now the same as the parameter itself. I'm not checking whether EAX is 0 or not. I'm checking whether what it points to is 0 or not. So the compare is comparing an immediate 0, but not with EAX, but with what EAX points to. Does everybody understand line 13 of the assembly code? Okay, all right. Because I'm not comparing to the parameter, I'm comparing to what the parameter is pointing to and whether that is 0 or not. In the conditional statement, it is saying if it is not, which means if it is null, I will perform these operations. If it is non-null, I will go to the else section. So that means I have to do a J and Z. If it is not 0, I would go to the else section. So go to else. And the way I usually do things is, as soon as I have a J and Z or any jump instruction, I would define the label. And I would also do a unconditional branch at the end of the then branch to the end of this particular conditional statement. So I would define all these labels right away, just so that the structure of the conditional statement is already in place. I just need to fill in the content of the then branch and also the else branch in this case. All right, so we can pick on just one of them, and in this case, I'm picking on the then branch. So we are now dealing with line 8 of the C code and try to implement it in assembly. I don't want to do anything about the left-hand side of the assignment. I need to finish the right-hand side first, and that is just a call to malloc with the size of a struct node as a parameter. If I want to be lazy, I'm not going to be lazy here. So let's go ahead and do it the long way. I'm going to move node underscore size, which is defined inside node.inc, and I'm going to move immediate that into EAX, push it on the stack, okay, because that becomes the parameter. Call malloc. I mean, malloc is just a subroutine, right? If you want to pass parameters to a subroutine, you push it on the stack, you call it a subroutine, and then we adjust the stack pointer. We add $4 to the stack pointer to reclaim the space used up by the parameter, which is now useless. And whatever it returns, it's going to be returned in EAX. So I need to store EAX to where proot points to. So this is the slightly longer thing that we have to do. So I'm going to move proot EBP, the parameter itself, into a different register. I can move it into ECX or EDX, so ECX it is. And once I have that, I can now save the return value, which is already stored in EAX, to where proot points to. But because ECX is actually proot at this point, I just need to use the indirect operand to store the result to where proot points to. Are we still doing okay so far? If you guys have any questions, let me know. Because most of the time I'm watching on the screen, I don't see any hands. Yep, go ahead and then. Okay,
So you called malloc and then added 4 to the stack pointer.
Mm-hmm.
Malloc puts it on the stack, right?
No, malloc returns the pointer through EAX. What I'm deallocating from the stack is the parameter itself, which is the size of the node.
So malloc returned to the stack?
No, malloc is just a subroutine in C.
Okay.
And all subroutines in C look for the parameters on the stack.
Mm-hmm.
And that's why I have the push instruction here. Line 16 is
okay.
pushing the parameter on the stack. But when malloc returns, that parameter is not useful anymore.
So you just
So I deallocate it.
Okay.
I do not have to, because the last instruction, which is move EBP to ESP, will deallocate any junk that I have on the stack. But I don't want to do it this way because it's just wasting stack space for no reason. Yep.
I was not seeing where the stack was balanced.
Yep, it's just to make sure the stack is balanced. In this case, if you do not have line 18 in the assembly code, it will still run correctly because nothing depends on the actual value of ESP, because I'm using EBP to access all of my parameters anyway. But you'll be wasting space on the stack unnecessarily.
It could cause problems if you didn't have the EBP.
Move EBP to ESP, then I'll have problem, because that is one move to deallocate everything that I use on the stack. All right, so we are done with line 8 at this point, and it's time to move on to line 9, line 10, and line 11. Okay, so all of these are referring to what p root points to, but I already know what is p root pointing to because that's just EAX, because I just put that into p root. So instead of using indirect EAX, I can just use ECX. Sorry, instead of using indirect ECX, I can just use EAX as this portion of the C code. Is that part okay? Yep.
So what is the node underscore size for?
Say please.
Node underscore size. Line.
Oh, that is just a label defined to be the size of a node.
Oh.
Yeah. So if let me just explain that one. If we switch back to node include generator.c, you can see the last entry is how we define the label. So it's basically just the size of a struct node. And you should do the same thing with your code, because in your code you also have a malloc in lstr read, so it's going to be about the same thing. So as I said, this may be helpful, when you're doing your homework assignment. Hint, hint, hint. All right, so now we are on to line 9 of the code here. And because EAX is really useful, I don't want to mess around with the value of EAX, so I'm going to use some other registers, if I want to copy stuff into an intermediate register. Okay, so in this case, I'm going to move the value of parameter v into register, let's say ECX, because I don't have use for ECX anymore at this point. So I'm going to move v EBP to ECX, and then I'll move long ECX to the member v of what p root points to as a pointer points to. So that's going to be node underscore v, which is the displacement from the beginning of a struct node to the member v. And because EAX is already pointing to a struct node, this is all I need. In other words, line 22 of the assembly code, or excuse me, line 21 and line 22 of the assembly code is accomplishing line 9 of the C code. Okay, let's take a pause here just to make sure that we are good with this, because the next 2 lines will be a lot easier. Are we doing okay so far? Because EAX is a pointer to the first part or the beginning of a struct node, so we just need to use the base operand here to refer to a particular member of a struct node. Okay, if this is done, the other 2 will be like really, really easy, because we're just putting a constant 0 to PL and to PG. Like so. Are we still doing okay so far? Okay. So the then branch is all done. It's time to move on to the else branch. The else branch has its own conditional statement, so we have to deal with the conditional statement first. At this point, okay, if I get to the else label here, EAX is still pointing to, EAX is p root, okay? So if I want to do this one here, I can actually do it relatively easily, because EAX is still p root in this case. So I'm going to move node underscore v EAX, because EAX is it is still a pointer. Nope, can't do that. I have to dereference it one more time first. Okay, let me just explain what I mean by that. EAX is p root, but I'm not using p root as a pointer here. P root is a pointer, but it is not a pointer to a struct node. P root is a pointer to a pointer to a struct node. So I need one more level of dereference before I can access a member. So I need to move indirect EAX to EAX to dereference it. So if I want to add some comment here, I can say EAX is now whatever p root points to. Then I can actually access the members. So now I can access member V and say, let's go ahead and copy node underscore V EAX to say ECX. So that becomes the right hand side of the comparison. Then we can do the actual comparison. The right hand side in C code goes to the left hand side in assembly code. And so the other one is just the parameter V, which is which is relative to EBP. And if it's less than or equal to, we go to the else branch. Okay, so we say, and I think V is a signed integer, so we have to use L or G in this case. Less than or equal to is not greater than, so JNG to the else label. Now this is where you have to be careful because we're already in an else branch. So if you want to indicate this is the else branch of an else branch, I personally just say else else, okay, because that is a way to indicate which branch of another branch, it can indicate the structure of the conditional statements without any possibility of collision. So I'm just going to do it this way. So else is here, and since I'm doing the conditional statement, I might as well finish the entire structure. So now I have and else if you find it here, and then this will do an unconditional branch to and else if. In other words, I'm doing the same thing as last time. I'm finishing up the entire control structure first, and then I go back in to fill in the content of the then branch and also the else branch. Line 31 is now corresponding to line 17 of the C code, which is a call to the subroutine itself. So, so the first thing I have to do is to push V on the stack. Now this instruction actually works. Okay, we can actually do it this way. Instead of putting it into a register first and then push the register, this actually works. But it is awful in a way because it's a cisp addressing mode to begin with, and then this is also a cisp instruction. So in a certain way, it is really handy because I don't have to write 2 lines of code to accomplish the same thing. But on the other hand, it is kind of nasty because I'm using a cisp feature, and sometimes I don't like to use cisp features. But this will do the same thing as moving V EBP into EAX first and then push EAX on the stack. That's our the second parameter. Then we can push the first parameter. Now the first parameter looks really, really nasty, right? Because we are looking at the address of a particular member PG of a structure that is pointed to by a pointer that is pointed to by proot. Okay, can someone repeat just what I said? Okay, so I'll say that one more time instead of rewinding the recording for today and just let me, let my recording do it again. Okay, so this is the first parameter to BST insert on line 17 is trying to push the address of, that's the ampersand, a member of a node structure, in this case is PG as a member, and that structure is pointed to by a pointer, and that pointer is pointed to by proot. That's basically what the first parameter is. Okay. And in situations like this, if you're good with this and you can kind of visualize what this is, that's good. But if you cannot, it doesn't hurt to draw a picture. Okay, so what I'll do is I'll draw a picture first. So proot is our parameter. It is on the stack. Okay, it points to another pointer. Okay, so this pointer has no name because it is just 4 bytes pointed to by proot, but this pointer in return points to a struct node. Okay, so this is a node. And within a node, we have a member PG. Okay, we don't care where PG really is. We just know that this is defined to be PG as a label. So we want to find the address of this thing here and pass it on the stack. That is what we're trying to do. Is that okay? So to do that, it means every time we have a link here, we have to do something in assembly code. okay, including this part here, okay, because this pointer technically points to the beginning of the entire structure. So we need another step to go to the particular member that we want to access. Okay, so looking at the picture, the next few instructions will make more sense. I'm not going to take any shortcuts here, so I'll start from proot just so that you can see the entire sequence of instructions. So the first thing we do is to access our parameter, which is proot. So we'll go ahead and move our parameter proot, EBP, because it's a parameter, it is always relative to EBP. And this time I will use EDX just so that we don't confuse this particular exercise with whatever we store already in EAX or ECX. So now EDX points to the unknown pointer, right? Because the proot points to the not unknown but unnamed pointer. And if we do a dereference at this point, move L, indirect EDX to EDX, that finishes the second link. So if I label these links here by the line number in the assembly code, this one is done by line 32. So line 32 will accomplish this step here. EDX will point to this location, which by itself is pointer. Line 33 will accomplish this step here. So that at this time, the EDX points to the base of a struct node. Now that we are at the beginning of a struct node, we just have to add the displacement from a struct node to its member PG in this case to EDX. Then it becomes the address of the member PG. So this third instruction on line 34 is accomplishing this link here. So this is line 34. And now we do have the address stored in EDX. It's time to push it on the stack and then call the subroutine. So are we doing okay so far with this code here? Is everybody kind of following the picture with the assembly code? So with your homework assignment, it is not, I don't think your homework assignment is as involved as this one here, but a picture always helps. Okay, if you want to look at a picture, it always helps. So now it's just time to push EDX on the stack and then call the subroutine BST insert. When BST insert returns, it is a good way. It's a good idea to reclaim the space used up by the parameters. Line 31 is one push. Line 35 is another push. Both are pushing long, so when I come back here, I can reclaim 8 bytes from the stack. Phew. Are we doing okay so far? More or less? Good? Okay. All right, so now we are handling the else branch of the else branch of the conditional statement. So this would be corresponding to line 19, which by itself is a conditional statement. This is actually the third level of conditional statement of this entire control structure here. But before we can do all the labeling, we have to do the compare, and this time we're looking for less than, which means if it is not less than, we have to basically go all the way out of and if. All right, so we are going to move L. Okay, I'm not going to take any shortcut, so we'll do it all the way from the beginning. So proot is now in EAX, indirect EAX to EAX. That becomes the pointer that has no name, but it does point to a okay, let me just highlight the code that I'm implementing, so that makes more sense. Okay, so now EAX is the pointer that has no name, but it points to a struct node, and we want to access the value of member V of that particular structure. So we'll just go ahead and copy node V of that structure to a particular register, let's say ECX. And then now we can do the compare. When you compare, what is on the right-hand side of C code goes to the left-hand side and vice versa. So ECX is now on the left-hand side, and the V, which is a parameter, and that's why we have to use EBP as the base register, is on the right-hand side. jump if not less than, because we are looking for less than for the then branch. If it is not less than, we get out of the then branch. But when we get out this then branch, we go all the way to the end of the entire conditional statement. Yep.
Can we use JZ also? Because we already know that it's
Yes,
nonce.
that will work as well. Yep. But I'm doing a completely, straight translation from the C code. But yes, if you do a JZ, it would work as well, because we know it's not greater than. Excuse me. We know it is less than or equal to, and then if we on top of that know it's not less than, it has to be equal to. Okay. And now we can just go ahead and implement the this particular branch. So it's the same thing as what we have earlier, which is all the way from line 31 to line 37. So I'll just be a little bit lazy. Specify line 31 to line 37, copy to the current line, and just be careful that we are dealing with PL in this case, because when you look at line 17 of the C code and line 21 of the C code, they are identical except for which member we are using on the first parameter. This one is using PG, this one is using PL, so I have to make that one change here. And that should be it. That should be the entire subroutine. Shall we give it a try? This is an awfully long subroutine before I actually do any type of testing. Okay, so this will be interesting. All right, so getting back to the make file, we have to indicate that we have BST insert implemented in assembly. Take out the reference in C. Change BST insert.c to something other than that extension. But the way I set this up earlier in the previous semester is that these are symlinks, so I can actually delete it. So I can just delete BST insert.c because I'm just deleting a symlink. The actual source file is inside the C subfolder, so I'm not losing the C file by deleting just the symlink to the source file. But this will convince the make file to that it needs to go to the .s file instead of the .c file to compile. So make clean. There we go. All right, so we have a problem on line 24. That's a serious typo mistake. Line 24. Those are the problems that I like. All right, it compiles. The question is, does it run? Okay. Now I'm going to do something that I do not recommend, but I'm going to do it anyway. I'm just going to run it. I'll test it by running it without using GDB first. So 4.1.25. So I've been exercising both branches of BST insert at this point because the way it works is it will construct a node first, and then all the subsequent nodes will be either on the left-hand side or the right-hand side, depending on the ordering of the new values. So by putting something that is less than the node and greater than the node, I'm exercising it to go on both sides. So I need a little bit more than this. Okay, so of the 25, I'm going to put one, on one side of the 25, which is 22, and then one on the other side, which is 27. I need to do this to make sure that the recursion part is also working. So I'm giving it, as many test cases as it is necessary to go through all the branches. If I messed up any type of pointer stuff, it would have crashed by now. Okay, because a BST insert is what is happening, at this point. Okay. And if I type Control D, the program is, exiting, and it prints out the numbers in a sorted way, which is 1, 4, 22, 25, 27, and it does work. And I am truly amazed. So other than the little percent, mistyping a dollar sign with a percent, the code actually worked the first time, which is uncommon for myself. 50-something lines of code and not make a mistake somewhere, that's pretty new to me. And no, I did not remember the solution from last time I talked about this, because that was 2013, May something? So that's a year and a half ago. I cannot remember something that I did last week. So are there any questions about this little exercise? Is it helping with your homework assignment? Yep. Okay, I'm glad it's helping. The picture always helps, okay? If you draw a picture, it always helps. But the key to draw a picture is to understand the C code first. And that really is, oh, I deleted the sim link, so I have to go to the C folder. And that really is the most important part, is to look at the C code and just take out one level at a time, okay? C code is not designed to be easy to read. Okay, you're not reading from left to right all the time, because in this case, you remember how I described this, right? It is the address of, but then we skip all the way to the member PG, and then we go backwards and say, oh, okay, is member PG of what? Is member PG of a structure, obviously, but where's the structure? It is pointed to, using the pointer structure here, or using the dash and the greater than, is pointed to by a pointer. But that pointer itself has no name. It is a pointer that is pointed to by p-root. So decoding the C code correctly, structurally, is the first step that is actually the most important part of writing code in assembly. Because once you decode the C code, then you can draw the picture. Once you draw the picture, then you can see that each time we have an arrow, it is just one or a few instructions to get it done. So that part is just kind of mechanical, but the part that understands the C code is going to be the most difficult part. All right, any questions? No questions? All right. So let me just double check on my website to see if I missed anything. This stuff, inline assembly code, it's not going to be, I'm not going to talk about it. It's just the ability of GCC to include assembly code without leaving C code at all. So, in the middle of your regular C code, you can literally insert a little chunk of assembly code. And that one little chunk of assembly code can refer to local variables, parameters, and so on and so forth. Okay, so there's a way to do it in just regular C code. So if there is one little thing that you need to do, and normal C code either cannot do it or not doing it the way you want it, you can actually insert your own assembly code right into the middle of a C code. You don't have to implement the entire subroutine in assembly most of the time. So it's kind of like a cool feature, but it's used sometimes by people who write drivers and other types of code where you do need low-level access to I/O registers, input-output registers. For most people, it's not it's not useful. Okay. Any other questions? Any questions related to all the stuff that we have? Yep, go ahead.
What would the inline assembly look like?
The inline assembly. Let's take a look. Not sure whether I finished this one or not.
I was just curious how we know where to begin and end.
Oh, okay. Well, in that case, you can just look up GCC inline assembly code and look up the Intel architecture. It's actually pretty, it's pretty interesting. It looks really kind of like that. And you can use these constructs here to refer to local variables, parameters, and other things. So this basically, when you use a double quote R, double quote, and then in parentheses a particular thing, it will stick temp into a register. It will force that particular value to be inside the register. I cannot remember the exact syntax. used this a long time ago, but I have forgotten how to do it ever since. But it's a directive, or it's a feature of GCC that allows you to use underscore ASM__ to specify a section of assembly code. And the nice thing is you can refer to local variables and certain expressions. So this expression 1 can be a really huge long expression, and the compiler will actually make sure that that part is compiled in C, and it will stick the value of that expression into a register, which is what the R is here.
It's kind of like a printf, somewhat.
Kind of, yeah. You can look at it as a printf. And then the other part of the code here, all the double quoted section here, is passed on to the assembler instead of the compiler. So the assembler will basically compile that chunk of code. It's handy sometimes. All right. So I don't think I'm missing anything too important. The only one part that I have not talked about that I think is kind of interesting is how to return an entire structure from a subroutine. Okay, and I can just draw a picture. We still got time. We have 4 minutes, so it's enough time to talk about how to return an entire structure. All right, it's best to use a picture for this too. And okay, so let's say you have something like this. Okay, struct X as the return type of a subroutine F. Okay, and to do this, you have probably something here to return, as a return value. So you're going to have struct X, RESULT for result, and then you can just say return. This is fading. Where's my other pen? Return result and close curly braces. So I'm just making this, making this up, just so that you can see that there are no parameters here. The return type is a struct X, and I have a local variable called result, which is also a struct X, and I'm going to return it. So the question is, how is this done in C on the stack? Okay. So we'll take a look, from the caller's perspective first. Okay. So the caller is actually going to reserve the space to store the entire return result first. So from the caller's perspective, it will reserve the space of a struct X somewhere, okay? Usually on the stack. But it's the job of the caller to reserve that space and then reclaim that space later on. And then in this case, if you have any additional parameters, okay, so let's say you have P1, P2, and so on as parameters, those will be pushed on the stack first. So P2 is pushed first, and then P1 is pushed next. And then the last one is going to be an address pointing to the beginning of the reserved space of the return value. And that one is implicit. It has no name, okay? When you do this in C, you only have 2 parameters, P1 and P2. So this parameter is basically hidden. It is not visible from C's perspective. And then all the usual stuff happens, okay? So you do the call, and then you have the return address on the stack because of the call instruction. From the callee's or the subroutine's perspective, it will save the old EBP, okay, to construct the usual frame. And then we have the local variable, which is a struct X. So we have struct X here, and this is actually our local variable result. Okay. So this is how the stack will look like by the time we get to the return instruction or the return statement in C. And the question now is, okay, so let's say you have some additional code here to deal with result. So result is not uninitialized, it is actually initialized to something. So how do you return the entire structure result to the return value that basically has no name? Well, the answer is pretty easy. You just copy the whole thing. You take everything here, you just copy it all the way back to the space here, using the unnamed parameter that's implicit. That is how it's done. Okay? And then after the return statement, this part will be deallocated, You have a pop EBP to restore the frame pointer, a return instruction to make use of the return address. So by the time it gets back to the caller, okay, this portion will still be on the stack from the caller's perspective. So what the caller would do at that point is to deallocate these three parameters, okay? Two are explicit, one is implicit. So all of these parameters will be deallocated, and you will only have, from the caller's perspective, on the stack, it will only have the resulting struct X as a return value on the stack at that point. It has no particular name, it is just sitting on the stack, pointed to by the stack pointer at that time. So the caller can now do whatever it wants with this thing here. In other words, if the call to F is on the right-hand side of an assignment operation, it would just be copied to whatever is on the left-hand side. Or this can serve as a parameter to another call, right? Because you can call another subroutine with a struct that is passed by value instead of a pointer. So this will be remaining on the stack as a parameter, and you can push other stuff on the stack, for that call. So that's kind of how structures are returned in GCC. And I believe in Microsoft C and other C compilers, it is about the same. They have the same, almost the same kind of idea of how to reserve a space and return a structure. All right. Any other questions? Yep.
Is the same sort of stack allocation utilized for other return types?
Anything that cannot be stored in a scalar would use this. But you can return a 64-bit integer using only registers with a 32-bit compiler. It is still considered a scalar with a 64-bit integer. But then you'll be using up two registers.
Straight on.
Yep, EAX and EDX. All right, so we are out of the lecture. We'll do the practice final on Thursday, and I'll be over at the lab if you are going to do your homework assignment. I can take a look at any potential issues